subvarieties, if this is embedded in projective space, you could always throw in many more equations to the ones defining x, and so you get continuous families of algebraic subvarieties. But you'd like to say that in some sense, some varieties are more or less equivalent to other ones. And yeah, the one notion of equivalence is rational equivalence. So I'll talk about Chow groups of X. So say with a subscript, the I Chow group means the free abelian group on the set of I-dimensional closed subvarieties, irreducible subvarieties of X. Modulo, in some sense, the sort of equivalence relation that identifies things as little as possible while still giving you some kind of manageable group. So you declare that two subvarieties basically are equivalent if there is a family of parameterized by just P1, by the simplest algebraic variety, the projective line. So with, from Y1 to Y2. That's a rather sloppy way of putting it. In particular, yeah, you certainly have to think about sort of sums of subvarieties and maybe differences of subvarieties, but that's the basic point. So for example, if you have inside X, you might have a I plus 1 dimensional. So these are I-dimensional subvarieties. What sort of equivalence relation am I talking about on them? Well, in particular, if you have an I plus 1 dimensional subvariety, say W, and you might have a rational function on there, which you can think of as a function from W to the simplest algebraic variety, like the numbers in your field union infinity. Then I want this relation to declare that the fiber over 0 should be counted as equivalent to the fiber over infinity. Because in some sense, there's you can connect Y1 to Y2 in the simplest possible way. Okay. So yeah. So then given this group, well, basically I'd like to ask when this is finally generated. In some sense, it's not very often finally generated, but then you can ask more interesting questions. So maybe one basic example would be that for projective space, these groups are very small. So the Chow groups of projective space are just, say, Z, if I is between 0 and n, and 0 otherwise. So in other words, although there are a ton of different algebraic subvarieties in projective space, for this equivalence relation, there are not that many of them. The proof being basically that in projective space, if you have any algebraic subvariety, so these groups I might say are like, so Chow I is a Pn is generated by an I-dimensional linear subspace of projective space. So by a linear Pi inside Pn. That's the generator of the Z. So in other words, I'm saying that, for example, any curve in projective space is rationally equivalent in that group to just some number times a line in projective space. And why is that? Well, it's basically because projective space has enough automorphisms that, let's say, you can just sort of scale this curve. So you draw a sort of family of curves getting closer and closer to this line. And in the limit, you do just get any curve squashed into some multiple of the line, the way these definitions work. That kind of crushing one algebraic varieties to so some multiple of another is allowed in this relation. So, okay. So that's sort of, for some algebraic varieties, these are small. On the other hand, rather often they're big groups. So let's see. Another sort of simple example would be that if X is an algebraic curve, then the Chow group of 0 cycles on X, well, let's see. It maps to the integers by taking the degree of a 0 cycle. So if this is X, an element of this child group is represented by a finite sum of points with integer coefficients, you could just add up the coefficients, and then the kernel is the k points of the Jacobian of x. So this is an abelian variety of dimension equal to the genus of this curve. Okay. And so the point I'm making is that this is often a big group. So for example, if k is the complex numbers, let's say, and the genus of this curve is at least 1, then this is an uncountable abelian group. So in other words, it's sort of different from just homology groups and topology, which would essentially, for reasonable spaces, always be finitely generated abelian groups. On the other hand, you might say this is kind of an understandable, I mean, it's uncountable, but it's kind of understandable abelian group, just the sort of points on an abelian variety, say complex points, if we're talking about k over the complex numbers. So, yeah. You can think of it as 2G copies of the circle group topologically. Okay, so because of this, it's not reasonable to ask whether child groups of complex varieties are finitely generated. They're just very often not. On the other hand, there are sort of interesting questions about, I mean, more subtle questions. So for example, one good question is, let's say, what about varieties over number fields, over smaller fields? So this is, I guess, called the motivic fast conjecture, or it's part of that conjecture. So if you have a variety, say smooth projective, over a number field, then you could ask whether child groups are finitely generated. Yeah, and I would say that's a very big open problem. It seems plausible, but it's very far from being known. Oh yeah, I mean, yeah. Let's say, yeah, of course. The answer's got to be yes. Let's say it that way. Yeah. So I mean, so one point to make about this is that just the way these things are defined, I could think about a variety defined over a number field, and then think about, in some sense, the same variety defined over the complex numbers. In other words, use the same equations, but think of it as a variety over complex numbers. And as such, its child groups would be different. I mean, because you know, in this definition, you're allowed subvarieties. You know, if we're thinking of x as a variety over k, then in some sense, here we're allowed subvarieties that are defined by equations with coefficients in k. So, so in other words, it's perfectly possible that a variety over a number field has child groups that are finitely generated, but when you think of the same variety over the complex numbers, they would become enormous, like in that example. Anyway, so this seems quite reasonable, in particular because there's one important case where this is true. So for example, well, I just say just this case of chow zero of a curve. Chow zero curve x, since, well, basically chow zero apart from this z group amounts to the group of k points on an abelian variety, and well, I mean, so it's just the Mordell-Weil theorem says that the group of points with coefficients in a number field on an abelian variety is finitely generated. A of k is a finitely generated abelian group. Okay, so you know, in some sense, that's very small evidence compared to the whole conjecture up there. But on the other hand, that is sort of a typical case where child groups, complex varieties are big, and this is somehow encouraging that over number fields they appear to be small. Okay, let's see. There's sort of entertaining variants of this question. So sort of, I guess, so I guess there's a sort of easy or relatively easy proposition that it's related to sort of the difference between what happens over number fields and what happens over a bigger field. So this is that, I've forgotten to prove this. Anyway, it's the fact that for any abelian variety over Q bar, so if I think of not just a number field, a finite extension of Q, but the limit of all finite extensions of Q, then abelian varieties in some sense have a lot of rational points. The group of points of A over Q bar, let's say tensor with Q, for example, has infinite dimension. So in other words, what I'm saying is if you take, say, an elliptic curve over Q, it will have some finite rank. And if you look at it over bigger number fields, I'm saying here that the rank always gets bigger and bigger eventually. So that even going just from a number field to Q bar, Chow groups in some sense become big. This thing, it has to be a countable group because there are only countably many points over a countable field. But anyway, it's sort of as big as possible given that. I kind of like this because there's a sort of a neat geometric explanation of this. By the way, this was apparently first proved by Fry and Yarden in the early 70s. So just to give a hint of it, so let's just show that for any abelian variety, or I want to specialize as much as possible to be concrete. So let's say for any elliptic curve, any over Q bar, say E, let's just show that E of Q bar has positive rank. Getting bigger and bigger rank is going to be just applying versions of this argument over and over again. So how can you do that? The picture is something like, think of an elliptic curve over Q as being something like a family of elliptic curves over respect of the integers. It might have become singular at some prime numbers. Okay. So, the group of rational points is the group of sections of this vibration. There's a zero section. And I want to argue that maybe not over spec Z itself, but over some some bigger number field, some ramified extension of the integers, spec of some other number field. I want this elliptic curve to have a section that's not torsion. That's what I'm saying. Okay, so why is that? Well, it's a nice picture, which is you think about a sort of maybe in general. So there might not be too many sections of this map, but there are always going to be sort of lots of multi-valued sections. Those things correspond to sort of sections of E over bigger number fields, and you want to argue that some such thing is not torsion everywhere. But I mean, once you see that that's what you're trying to show, it's not so hard to force something like this not to be torsion. All you have to do is make sure that it's torsion at one prime number, say of order 2, and torsion of some other order, say 3, at a different prime number. And then in some sense, then you were done. Let me say it like this. So here's my family of elliptic curves over the integers. Let me just draw a section instead of a multi-section. Suppose I have a section that's, so this is a point of order 2, say, over one prime number. And suppose that it's equal to a point of, this is supposed to be the 0 section. Suppose that my section is a point of order 3. At another section, well then, that implies that this section cannot be torsion. I mean, there's different ways to say this, but basically it's because if this thing was going to be section, let's say, a section that's of order 2 at one prime number, I claim it's either got to be of order 2 or of infinite order. It's certainly not of order 2 because it's of order 3 at this other prime, so that will argue that it has to be of infinite order. So let's say, why does it have to be of infinite order? Well, you basically think about the torsion points on this family of elliptic curves. I mean, that's sort of a countable set of different points that you're allowed to hit. And if you are of order 2 at this point, and you start, so either you're going to stay of order 2 at all points, or you have to sort of wander off from there. And then in this picture, it's clear that you have to be of infinite order. Yeah, there's a way to be more careful about that, but I mean, I hope it's clear from the picture that once you start wandering off from this, from being of order 2 everywhere, then you're not going to be a finite order of any finite order. Okay, sorry, I said that a bit messily. Okay, so let's see. So specifically in this talk, I wanted to talk more about, sort of a different line of questions about sort of the Griffiths group, which is just sort of about part of the child group. Okay, so I turn to, so if you think about complex varieties, as I said, the child group itself is not going to be finally generated very often. But you can, in some sense, look at the discrete part of it, which has sort of more of a chance to be finally generated. So, so let's say, so inside the child group of, say, for X over an algebraically closed field, that's where this is reasonable thing to talk about. Let's see. There is the subgroup of cycles that are so-called algebraically equivalent to 0, which means cycles that you can connect to 0 by a continuous family of cycles. So another way to say it is, in the definition of rational equivalence, you're basically starting from the by declaring that any 2 points in P1 should be considered equivalent to each other. With algebraic equivalence, you consider the same notion, but with considering any 2 points in any curve as being equivalent to each other. So if I have any family of algebraic subvarieties parameterized by an algebraic curve, I declare that this variety is equivalent to that one. That's the notion of algebraic equivalence. That's sort of much cruder equivalence relation. In particular, it's more or less easy to see that child groups mod, let's say for a complex variety, mod algebraic equivalence, that's easily seen to be a countable abelian group. Just because anytime you have a sort of continuous family of algebraic varieties, they all count as being equivalent in this group, and so it's kind of easy to see that what's left is just something discrete, something countable. Okay. And the question I mostly want to talk about is when is this group finally generated? That's sort of a more reasonable finding-this question for complex varieties. Okay. Right. So of course, Griffiths showed that this. So maybe there's a. So in particular, cycles that are algebraically equivalent to 0 count as being 0 in homology. So let's see. The Griffiths group of a variety over an algebraically closed field means cycles that are homologically equivalent to 0. Modulo the ones that are algebraically equivalent to 0, the ones that you can connect to 0 by a continuous family of algebraic cycles. Homologically equivalent to 0 just means those that map to 0 in ordinary homology. So child groups of a, say, complex variety map to just ordinary homology in dimension 2i, because I-dimensional complex subvariety has real dimension 2i. If you have a cycle that you can move to 0 in a continuous family, then it certainly maps to 0 in homology. And one could ask about the difference. I guess Grodnik asked whether this group was actually 0, and Griffiths showed that the answer is no, this can be non-zero. So this group can be non-zero, even tensored with irrationals. Okay, and so his example was you take a general clinic threefold that is hypersurface in P4 defined by an equation of degree 5 and take the coefficients of that equation to be general, that is, throw out any special cases that cause a problem. And in that situation, then X contains a finite number of lines. In general, it will contain 2875 lines, typically disjoint, copies of P1. So they're all equivalent in terms of homology. So we have H second homology of X is just Z times any one of these lines. Right. But it's not obvious that you can connect two of these lines by a continuous algebraic family. In fact, it's quite easy to see that you can't just find a continuous family of algebraic curves that moves from one of these lines to another. I mean, those curves would all have to be lines, and there are just these finitely many. But it's not so obvious that even allowing things like, could it be that this curve plus some other curve is rationally equivalent to, say, or algebraically equivalent to this, some other line plus the same curve? In other words, by taking differences, it's not so clear whether these lines are algebraically equivalent or not. But Griffiths showed that in general, they're not algebraically equivalent. So Griffiths difference of two lines in X, assuming X is sort of general enough, is not zero in the Griffiths group of X. In other words, the key issue, he showed that typically any two of these lines are not algebraically equivalent to each other. Okay. So that was sort of disturbing enough, but then Clemens went further and showed that actually the Griffiths group doesn't even have to be finally generated. It's obviously countable, but it doesn't even have to be finally generated. In fact, for the same example for X, a general clinic, the Griffiths group tensor Q, it's definitely countable rational vector space, but it has infinite dimension as a vector space. Indeed, but I'm not being very careful. Yes, if we want to be careful, yes, that's true. So, not I think in this case, but I'll maybe say something about that. Yeah. Right. Okay. So I just want to say sort of. So in other words, so what this is saying is that somehow there are for this algebraic variety, this threefold, there are infinitely many algebraic curves that are somehow genuinely independent, even apart from sort of, even if you're allowed to move one curve continuously to another curve and take differences of curves and so on, there are infinitely many curves that are genuinely independent on this variety. So it's sort of quite a novel phenomenon. This is around 1969, and this is around 1983. Okay, so what are the curves he used? So it's similar, but you can't use just lines. But he just looked at rational curves of arbitrary degree. So this is a famous sort of a variety in various situations, like in mirror symmetry. This is its canonical bundle is trivial, or first Chern class is zero, which in some sense means that it's kind of right on the edge between, well, obviously, between sort of positively curved varieties like projective space and negatively curved varieties like curves of genus at least 2. In some sense, because it's right on the edge like that, it doesn't have a continuous family of rational curves, but for any given degree, it's at least expected to have a positive number of rational curves of any given degree. So you might famously point out that Candelas and other physicists predicted that they explicitly computed the number of rational curves of any given degree counted appropriately. So this is sort of a virtual count, and exactly how real it is not completely known. But nonetheless, you can show that for a general threefold, you may not know exactly how many rational curves there are, but there are infinitely many sort of discrete ones, the ones that have normal bundle, like O of minus 1 plus O of minus 1, which in some sense means that these are rational curves that don't move around continuously. And so it's sort of plausible that they might be independent mod rational equivalents, but that is in fact what Clemens showed. Okay. So I mean, I guess it's kind of interesting to think how this is related to what could be happening over number fields. So, for example, over number fields, if you consider such a variety over a number field, its Chow groups should just be finitely generated. So, what happens to all those curves? Well, there's sort of a plausible explanation for what's happening, which is that, for any given positive integer d, you could look at sort of the union of all the rational curves of degree d, and that will be defined over q if your variety x is defined over q. But any one of those curves is only going to be defined over some finite extension of q, because the Galois group of q will permute those curves around. And it seems that what's happening is that over any given number field, you'll only see some of those rational curves. If you look at bigger and bigger number fields, you'll see more and more of them individually. But in some sense, that's a plausible story about how the Chow groups over number fields might be finitely generated. Okay. Right. So yeah, there's maybe I should say that Claire generalized this quite a bit in a certain direction. So, so if you take any Calabi-Yau threefold, so I suppose that means that the first Betti number of x is 0 and the canonical bundle is trivial. And non-rigid means that just if you consider the moduli space of all deformations of this variety, that you're assuming that moduli space has dimension at least 1. So which is certainly true for clinic threefolds. You can vary the coefficients of your clinic polynomial, and you get a continuous family of different complex manifolds that are all topologically the same. Anyway, just with that assumption, then a very general, as you say, variety x in this family of deformations of x has Griffiths group tensor Q of infinite dimension. And I guess it's plausible that this might be true for the same reason that we expect varieties like this to have a lot of rational curves, but in fact, in this generality, we don't know that these varieties do have a lot of rational curves. So she had to use a different class of curves. So I mean, basically, sort of one key issue in proving anything like this is you have to produce infinitely many interesting algebraic curves on your variety, some curves that are not related to each other in a simple way. I'll describe what she did. So, okay, so in that example, how are you going to? Of course, it's quite a general class of varieties. You don't have a very explicit geometric control of these varieties. So somehow, how do you produce infinitely many interesting curves on a variety that you don't know much about? Okay, so her idea was to use Noether-Lefschetz loci, which I think is not as intimidating. I mean, something rather natural in terms of Hodge theory. Right, so what's the deal? You consider such a variety, a Calabi-Yau threefold. I imagine it's embedded in projective space, and consider the family of all the hyperplane sections of that. Okay. So if X is embedded in some fixed projective space, you can intersect it with all the different hyperplanes in there. So I mean, all these curves will be all these surfaces rather. This is dimension 3, so these complex surfaces. All these surfaces are rationally equivalent to each other, so sort of they're not differing from each other in an interesting way. But the idea is you can look at, for each of these surfaces, what's the group of algebraic curves on there. And what will happen is that sort of for most of these surfaces, there won't be that many interesting algebraic curves on there. But you know, sort of for countably many surfaces in this family, you can argue that the group of algebraic curves on there will jump up. That's so let's say the rank of the Chow1 of the surface mod homological equivalence will jump up. In other words, for countably many surfaces in this family, there will be some sort of unexpected algebraic curves. And so, yeah, for most of the surfaces, there's sort of nothing interesting, but for countably many cases, you get an interesting curve. And yeah, she's able to argue that those actually are independent mod algebraic equivalents. Okay, so these resulting curves, Ci in the picture, are independent mod algebraic equivalence. I mean, it's a colloquium talk. Maybe I can get away with saying just that. Okay. Right. Yeah, and I think there's no particular reason to expect those to be rational curves. It seems like this is just a different source of interesting curves. Okay. Okay. So, okay, let me discuss one more example where Griffiths groups have been shown to be big. I mean, yeah, so this is just maybe the simplest example. Where Griffiths groups are non-zero, and in fact, where they have infinite dimension. This is just abelian varieties of dimension 3. So principally polarized abelian threefolds. So again, topologically, it's just product of 6 copies of the circle group, but with the structure of a complex manifold. So yeah, in this case, Nori showed that that this Griffiths group has infinite dimension. So again, you've got to write down some infinite set of somehow interesting independent algebraic curves on these varieties. My varieties kind of always look the same, unfortunately. So let's see. So in this case, the basic source of an interesting curve on there is this so-called Teresa cycle. So right. So let's see how to describe that. So sort of one picture in the background here is that abelian varieties of dimension at most 3 are sort of simpler in a crucial way than abelian varieties in higher dimension, which is that if they're principally polarized, then they tend to be a Jacobian of a curve. Right. So the dimension of the moduli space of curves of genus G is 3G minus 3, and the dimension of the moduli space of, say, principally polarized abelian varieties is, I guess, G times G plus 1 over 2. So usually there are many more abelian varieties of dimension G than just the Jacobians, but for G equals 3, those problem numbers are equal if all things, if I'm lucky. Yeah, it looks right. Sort of most principally polarized abelian varieties of dimension 3 are, in fact, Jacobians of some curves. Okay. So for that reason, that sort of gives you, if you view a given abelian variety as the Jacobian of some curve, then you can imagine embedding the curve into its Jacobian. Standard way to do that. That curve is not zero in homology, but there's a trick which Theresa considered, which is to consider C minus, where this is the image of C under the map x goes to minus x on the Jacobian, on the abelian variety. So yeah, I embed the curve in such a way that the image contains 0 in the abelian variety, and then this curve minus this curve. The point of doing that construction is that it's easy to see that these two curves are in the same homology class. So yeah, so this is a cycle somewhere in the Griffiths group. It's am I saying this right? Yeah, that's a cycle which is homologous to 0, and it's not obvious whether it's algebraically equivalent to 0 or not. There's no obvious way to move continuously from one of those curves to the other. Okay. Right. So in fact, it's again for a general abelian variety. This Theresa showed that this class is actually non-zero in that group. Let's see. Okay. And then there's the issue of, okay, so there's one cycle on an abelian variety, or one interesting curve. How do you get infinitely many? So it's a simple point that you can just consider isogenies from your principally polarized abelian variety X to just other principally polarized abelian varieties. So, isogeny just meaning a homomorphism of algebraic groups with finite kernel. So this group, it has lots of finite subgroups. In many cases, you can arrange that the quotient abelian variety is again principally polarized, and then this variety will again typically be the Jacobian of some other curve of genus 3. Here you have the Theresa cycle there, and you can just pull that back. So gives sort of another elements of the Griffiths group. Okay, and Norrie's theorem is just that if you apply these infinitely many different isogenies, pull back the Theresa cycle, then you get infinitely many independent elements in the Griffiths group for most abelian varieties of dimension 3. Okay. Yeah, so I would say, to me, that seems like, and in fact, the proof is probably easier than the other, for the other examples of showing that the Griffiths group is big. This is quite probably the easiest approach. Okay. Yeah, that's right. Oh, right, sorry. You were asking that again. Yeah. So I think the first examples over number field are by Schoen. This is 1986. Well, to put it briefly, there are threefolds x over q bar with Griffiths group of infinite rank. So yeah, again, it's sort of quite. I think all the examples where you can do this are quite pretty geometrically. So his basic idea is you consider a family of abelian surfaces now fibered over a curve. So yeah, basically the situation is X is abelian surface fibration over a curve. And okay, so there might be some singular fibers, but typically the fibers are smooth abelian varieties of dimension 2. And where do you get the infinitely many interesting curves in this picture? You just contemplate which of these abelian varieties have complex multiplication, essentially. So, yeah. make the the simplest way to make such an example would be start with an elliptic vibration over curve and just take the self product of that with itself. That gives you an abelian surface vibration. And then just think about which of the elliptic curves in the family have complex multiplication. Well, you have a map from this curve to the moduli space of the elliptic curves, which has dimension 1. So you will hit pretty much every elliptic curve. In particular, you will hit all the countably infinite set of CM curves. So anyway, you can arrange that sort of for countably many of these curves, these abelian surfaces will have complex multiplication or otherwise be special, and that means that they have sort of some extra algebraic curves on there which you wouldn't have on a general fiber. So the CM cycles in the fibers you can arrange to be independent. Okay. I mean, sort of even for x over q bar. Again, you sort of need a sort of more number theoretic argument. Anyway, but I won't try to discuss details of how you do this. But anyway, it has been done. Okay. Yeah, I think in all these, I mean, sort of this kind of example, you can imagine playing with in many different ways. Like, I mean, this phenomenon that sort of inside the moduli space of all elliptic curves, there's this interesting countable set of points, the CM points, that sort of generalizes, to Shimura varieties of any sort. And, there are a lot of cases in number theory where you get kind of something interesting happening a countably infinite number of times, and you might imagine that this kind of phenomenon generalizes a lot. Okay.
Are there high dimensional?
I think there are, yes, right. But I mean, I'm not able to list them. But yeah, I think there are some higher dimensional examples. Of course, maybe not a lot. Anyway, sort of, yeah, the last direction I wanted to go was to talk about Chow group's modulo a prime number. So modulo L for, say, let's say x smooth projective over the complex numbers and L prime number. Right, so the point being that, well, if Chow groups were finitely generated abelian groups, then these quotient groups would be finite. Yes, in particular, I mean, the answer is no in general, not to drag out the suspense. But the point is that for many, many complex varieties that you can write down, these quotients will be finite. Like, for example, for an algebraic curve, sort of a big part of the Chow group is the points on the Jacobian of the curve. And in that case, if you divide out by a prime number, you just get 0. Sort of, so more generally, if you talk about the group of cycles algebraically equivalent to 0, mod rational equivalence it's inside the Chow group, and talk about that modulo prime number, then you just get 0. So sort of this whole sort of uncountable part of the Chow group's modulo prime number just disappears for complex varieties. So yeah, it's not so easy to give examples where this group is big. But that was done also by Shane. Let's see. So there is a threefold x over c with Chow group of codimension 2 cycles or one-dimensional cycles modulo prime number infinite. So his example, in one way, it's very nice that this variety you can make very explicit. On the other hand, it was frustrating that this only worked for all prime numbers congruent to 1 mod 3. So somehow, once you find that these groups can be infinite, then surely they should be infinite for every prime number. But with his initial example, that wasn't clear. So his example was just x is the product of 3 copies of an elliptic curve, just the Fermat cubic curve, about as simple as you can get. The point being that you have to consider this over an algebraically closed field. So again, that's obviously a variety over Q, and if you looked at his Chow groups over Q, they should be finally generated, but over C or over Q bar, you find that somehow there are a lot of interesting curves on this threefold. Okay. So I guess I'm not really managing to say much about how you're proving this, but yeah, maybe just let me go on and discuss a few more examples. So it sort of seems as though probably these groups should be infinite modulo a prime number pretty much every time that the Griffiths group has infinite rank. It seems like sort of the same phenomenon. The sort of confusing thing is, I mean, usually you prove that the Griffiths group is big by showing that the image of the group map from algebraic cycles to the intermediate Jacobian of X has infinite rank. But when you do that, somehow it's not so obvious how to show that these groups modulo prime number are infinite, because there's the weird possibility that the image might not be, say, something like a Z. It might be something like Q. It might be that every time you have a generator of that group, there's also a cycle that represents half that generator and a third of that generator. That seems absurdly implausible, that there should be all these cycles dividing other cycles by a fraction. But it's hard to rule out, and that's why, well, this example just the original example took really a lot of hard work. Maybe the fundamental idea is that you sort of, there's an analog of the intermediate Jacobian in number theory, which is just, given a cycle on a variety over number field, you can get a class in some kind of group like this. Somehow there is a group in number theory which plays the role of the intermediate Jacobian. And somehow this, in number theory, there's sort of really this theory sort of works integrally. And so it's not as hard to show that the image of something is non-zero mod L here as it would be up there. That's sort of saying something very sketchy. Okay, anyway, so this result was, sort of a simpler construction of the same sort of phenomenon was done by Rosenjohn and Srinivas, who showed that sort of with the idea that Norrie's example was the simple one to try to imitate. So they showed that for a, I guess, very general, principally polarized abelian variety of dimension 3, say over the complex numbers, the Chow group of codimension 2 or one-dimensional cycles mod L is infinite, actually for almost all prime numbers L. So unfortunately, this was not explicit, but for all but finally many prime numbers, they could show that these groups are infinite with sort of roughly the idea that I'm saying, that you can imitate arguments about the intermediate Jacobian with this kind of arguments about this kind of group in number theory. And they were able to basically argue that, so in that case, the sort of interesting cycles are these Teresa cycles, and you argue that, at least for most prime numbers, the class of the Teresa cycle in this sort of group will be non-zero mod L. Okay, so let's see. Okay, so what I've been doing for the past week is sort of fine-tuning their arguments so that actually it does work at all prime numbers now. So let's see. So for X very general, principally polarized abelian variety of dimension 3, then this Chow group mod L is infinite for all prime numbers. Okay, and this is, so in particular, to do this for the prime 2 sort of looked painful originally. Part of this argument is a little bit of p-adic Hodge theory. I should say something about that. But somehow the issue is, if you want to understand like which rational cohomology classes on a variety are algebraic, then Hodge theory, in the usual sense, is a good tool for doing that. But somehow, for these questions about working questions algebraic cycles mod L, you're led to questions like when is a Z mod L cohomology class algebraic on an algebraic variety, and sort of Hodge theory, as it's written, says nothing about that. But if you imagine reducing your variety modulo a prime number L, think of it as even if it's defined over the complex numbers, you can imagine as being defined over some big finally generated ring and reduce it modulo some prime number. You know, then sort of L-adic Hodge theory says something about the relation between homology with mod L coefficients and Hodge theory, groups like spaces of sections of differential forms. So somehow that's sort of a crucial ingredient in here is so they were able to use a sort of an old part of p-adic Hodge theory. Maybe I should say L-adic Hodge theory, but sort of for that prime number L, somehow questions about this child group of this complex variety mod L reduce in some way to questions about the variety reduced modulo prime number L, and also I should say Bloch and Ano's were kind of applying that p-adic Hodge theory. Yeah. So somehow this is, I mean, sort of an interesting connection that, you know, for this sort of question about complex varieties, you want to understand child group's modulo prime number, then you're somehow forced to think about number theory, to think about that variety reduced modulo L, in fact. Right. Okay. So let's see. I don't actually have a conclusion, I guess. I mean, it would be nice to understand all these things. You know, let's say how sort of the opposite conclusions happen over number fields, like, you know, showing that these groups are finite for varieties over number fields, but that seems kind of far off. I guess where it is true. There are a few, yeah. So let me summarize. So like, for example, Kato and Saito showed that if X is a maybe regular scheme, a finite type over Z, then the child group of 0 cycles on X is a finitely generated abelian group. That's sort of one of the few cases that's known. I mean, there are sort of slight, maybe several of the known cases that where we have good information are related to groups of 0 cycles like this. That obviously, in some ways, they're simpler than other algebraic subvarieties. So Kurtz and Saito have sort of other finiteness results on, let me say, motivic homology of X with finite coefficients. In some sense, generalizing. You know, they don't know this for. We like to show that all these motivic homology groups are finite. The ones which we can actually do are the ones that are in some sense related to 0 cycles. So, but I think, you know, that's pretty close to the size of about what's known. Oh. Like when these things. Oh, I think all number theorists expect that these are true. I mean, let's say it's related to questions about like orders of vanishing of L functions. Basically, you know, the rank of these child groups should be the order of some L function. You know, so they definitely should be finite. I mean, like you know, let's say. Oh, I see. Yeah, yes. Yeah, right. Maybe I see what you mean. I mean, not obviously, but maybe this is a little bit of the flavor of like, but maybe I think there's some kind of hope because, like, for example, this is a little bit like Falting's proof of the Mordell conjecture. You know, you reduce to some kind of Arakelov theory, or the Mordell-Day theorem, in fact, reducing to some kind of showing that something is finite where there's a geometric reason for it to be finite. I mean, I think there is some kind of hope for that. There have been some recent, maybe some recent progress, which is related as people have recently proved the Tate conjecture for K3 surfaces over finite fields, and it does have a little bit of the flavor of what you're saying. But you have, you know, some set which is a priori not finite, you manage to show for some reason that if it is. Yeah, okay, but I better stop.